So last time we worked out that even with time evolution, if you have a solved quantum system, eigenvalue problem for the Hamiltonian, because of the Hamiltonian's role in time evolution, if the system is prepared in one of the eigenstates of the Hamiltonian, then any observable property you can imagine calculating will not vary as a function of time, right? So let's just remind ourselves what we found. If the initial state is one of the eigenstates, then any operator will not be a function of time, the expectation value of it. All right, that's why we call these things stationary states, because they're stationary, they don't change. There's a time evolving phase that we cannot observe experimentally any other way. All right, so now what we want to do, of course, is get beyond this. We want to see what happens. How do we get things to evolve? How do we get things to change? So the way you get things to change is you make superpositions. All right, so let's do that. So we're going to start out with our system in a superposition of two quantum levels. And rather than the square root of 2 one that I did before, I'm going to pick 2, but I'm going to make the arbitrary, I'm going to make the coefficients arbitrary. So we're going to call it Cm for the state m and Cn for the state n. 2 is fine. Anything more than 2 is not going to make a lot of difference. There'll be more wiggles, more oscillations, and it'll be more complicated. This one is pretty straightforward. Okay. So what we want to do is calculate again the expectation value of some operator. It's a function of time. So we know how to do this. I'm going to skip to I'm not going to skip too much. I just want to minimize the repetitive writing that we do. Remind ourselves that psi of t is going to be u operating on psi of t naught. So we can write that down directly. Psi of t naught, u dagger for the left-hand side one, a. Oh, I should write the times in. I try to keep the time writing in there as much as possible. Sometimes you write so many of those things that you feel bad for the ink or your hand. All right, this is the same thing we wrote last time because this is very general. What's different is we're going to plug in this superposition state into here and here, whereas before we only had one of the eigenvectors of the Hamiltonian. So what we need to do is we need to work out this product first. Because we remember already that this is the complex conjugate of this, right? They're related by the Hermitian conjugation. We don't need to do it twice. Once is good enough. Okay, so let's do it once. So u operating on psi, we can write like this. Well, maybe I'll switch colors just for the heck of it. Okay. Is e to the minus I over h bar, h t minus t naught, operating on our initial initial state, which is Cm phi m plus Cn phi n. All right, so this is u, and this is psi of t naught. All right, so we know what this does. This exponential operator of h operating on this eigenvector replaces the h by the eigenvalue, em. This replaces the eigenvalue by en. The numbers are just numbers. They're going to be complex. We'll let them be complex. All right, so we distribute this in here. And what we end up with, we get Cm. That doesn't change. We get e to the minus I over h bar, em, t minus t naught, operating on phi m. That's the first term, plus Cn minus I over h bar, en, t minus t naught on phi n. Okay, see, all we do is replace this operator expression with this complex phase. It's the relative sort of spinning of these phases and their summing that leads us to have the destructive and constructive interference that causes the motion. All right, so let's take a look now. I make a little not a simplification. Let's make some notational change here. I'm just going to call the term that with the m's, okay, I'm going to call that term 1. The term with the n's, I'm going to call term 2. There's a lot of terms, right? We don't want to screw anything up. Okay, so what we do to calculate the expectation value, right? What we do is we write down the same thing. We put the A, we have these two. We know 1 and 1 star. So this is going to equal now 1 star A, 1, I'll write it out one more step than this. All right, just so everyone sees where this is going. There's nothing magic. Really, we're just following through on the very basic set of mathematical rules. So that's the left-hand side, the adjoint. So it's 1 plus 2, and the whole thing star, times A, or operating multiplied by A, and then we have over on the right-hand side 1 plus 2, without the star. Okay, so let's work out these 4 terms, right? You're going to have I star A I. This one, this one, this one. And then you're also going to have I star A 2. Then you're also going to have 2 star A 1 and 2 star A 2. Now, a few things that we should notice. One thing that we noticed, I hope already, is that we have this term here and this term here. Both have the 1 and the 2 in them, right? Which they only have the 1 and they only have the 2. So these will look exactly like the problem we worked out in the previous lecture segment for a single eigenvector, right? Because what's the vector part of 1? Phi m. What's the vector part of 1 star? Well, it's phi m also. It's just it's the dual. Same thing here. So we already know how to work this out. We don't need to do it again. Anytime they're the same one, it's just going to be the expectation value or the matrix element of A for the particular eigenvector we're talking about. Right? So those are like the easy terms. This is going to be A for the one case MM, and this is going to be A N N. Now, there's a little bit of a difference. What's in there? These are there. All right? So we're going to have 1 Cm on the left, Cm star, and on the right we're going to have Cm. So we have also Cm modulus squared. If you don't remember, where should I write aside things? If Z is a Z is a complex number, so it's like A plus IB, for example, then Z star Z is equal to A minus IB times A plus IB, and this is equal to the modulus squared of Z. Okay, that's just what we call it. It's A squared plus B squared. All right, so that's the sort of easy term. Same thing over here, CNN squared. One thing you'll notice with these, it's not CNN, just CN. I watched too much news, maybe. All right, so CN squared. Notice that there's no information about the complexness of Cn and M. We would say that there's no information about the phase of how you prepared the initial state vector. All right, so the harder terms are this, but also notice that they have an interesting symmetry. This one here is this complex conjugate of this one here. How do I know that? If I write 2 star A1 and do the Hermitian conjugate of that, I would swap the order and star things. A doesn't need to change, it's a Hermitian operator. Right? And that's exactly what this is. Right? So these are complex or Hermitian conjugates of each other. That means we only need to really work out one of them. It's easy to figure out what the other one is once you've figured out what one is. So let's do I star A2. All right, well, I star is just this star. Now, when we say star, of course, we mean, really, it also means switch this to a ket. Switch it to a bra. But we're just going to change the I to minus I, and Cm goes to Cm star. So we have Cm star. We have E to the plus I over H bar, Em. That's the number. And I'll just do it this way. It's going to make it not quite as clean as if I had done it pulled the numbers out. Okay, that's 1 star, then A, then 2. Why don't we just slide the vector over and put the number on the other side? So we have phi n. Remember, we can slide them like the Tetris, but they can't go through. Then we have Cn, no stars anymore. We're done with stars. All right, so now we sort of repack. All right, what do we notice here? We've called this a matrix element, right? It's going to give us a number. It's closed up. You have an arrow on the arrow, so that means whatever's inside of this is a number. Could be complex. And remember, A is not necessarily A does not necessarily have the same eigenbasis as H. So we don't know necessarily what this is, but we call that AMN, a matrix element. Okay, it's a number, we can float it around. Everything can move now because they're all numbers. There's no more operator stuff here. So we have Cm star Cn. We have AMN. And we have the exponential stuff, which we're going to combine now. All right, what do we see? If you have to pick, maybe it's good to pick a style in your life. If you like to have negative exponentials or positive ones. I don't really care. So let's just do negative. I'll do e to the minus I over h bar. That means that this one's the positive one. So I'll have en minus em t minus t naught. Right? Because I need to get this minus minus to get that plus there. All right, so notice this is the first place where we see delta E, which I can call delta E nm, which is just going to be equal to En minus Em. All right, now I can make this even simpler. I can call omega nm equal to delta Enm divided by h bar. And then this whole equation gets really simple. Cm star Cn, and we'll let t not go to 0. That's fine. We have AMN, the linear algebra part of our problem. And we have e to the minus I. The h bar is going to go away because we're going to suck it into this omega. Omega n m t. Okay. Pretty good, huh? All right, so what you see now is we have a potentially complex number that's determined by our initial superposition state. We have our matrix element. And then we have this time-dependent phase. And the reason why it stays is because these two energies are different from each other. It goes away when they're the same. All right, so when we put this whole thing together, which we can now do, and with the compact notation, you can fit it in a small space, we have the expectation value of A. It definitely depends on time, as long as these two states are different from each other and have like amplitude. we have the two what you might call intensity terms, the terms that don't have any interference between them. Those are the 1A, 1 star A1, okay, which we worked out already. So that's AMM CM squared, mod squared. This, by the way, is equal to the probability that the system is in the state M, plus the other one, NN CN squared, plus these, what sometimes people will refer to as cross terms or interference terms. We did 1 star A, let's write it again. CM star CN AMN e to the minus I omega NM T plus the other one, the complex conjugate of this. So that's CM CN star AMN ANM, right? We switch this will switch. And we have e to the plus I omega NM T. Okay, now a couple things to think about. First of all, you might be worried about all these i's. It's like, oh, there's complex numbers and I'm supposed to calculate the expectation value of this Hermitian operator, which is supposed to be giving me real things. What's the problem here? So you just have to keep track of the fact that this term here is equal to the complex conjugate of this term, fact number one. Number two, this is definitely real, this is definitely real, and the expectation and the matrix elements of A will also be real. All right, so because of that, because what is a matrix element, whatever it does, you're gonna get one value or some subset of values of the eigenvalues of A. If you convert this to the basis of A, then it'll just pick out all the eigenvalues of A that correspond to whatever this superposition state of A's eigenvectors gives you these 5 n's. We'll do examples of that. These are real. What about this? Well, here's this number plus its complex conjugate. So if you take a number like Z and you add its complex conjugate to it, you get A plus IB plus A minus IB. And lo and behold, what happens? The imaginary term goes away and you get 2A. All right, so in fact, a number plus its complex conjugate is equal to twice the real part of that number itself. So this part here is absolutely real. So we can rewrite this even more compactly as AMM CM squared plus ANN CN squared plus twice the real part of, pick one, CM star CN e to the minus I omega NM T. Okay, and depending on the values of Cn and Cm, it might be a cosine, it might be a sine, or some combination of cosine and sine, but it's going to oscillate, right? And that shouldn't be too shocking because if these are numbers, for example, if we had done the 1 over root 2, right? And we know that these are complex conjugates. If A was real and we knew this was 1 over the square root of 2, this would trivially be a cosine because it would be this plus this, which is just 2 times the cosine. Right? It doesn't matter if it's literally a cosine or not. The point is that we're going to be able to we see immediately right now, the key quantity is this. It oscillates. The frequency of oscillation is given by the energy gap. That is literally the basis of spectroscopy. But it's not just spectroscopy. It's all motion in quantum mechanics comes from this kind of superposition of states. These superpositions rely on the very precise phase of these two. And as you can imagine, if you come along in the world somehow and make a superposition of two states, any tweak, any collision with the environment or whatever is going to cause that superposition to break up a little bit and get lost. So that's a process that we call dephasing or decoherence. It sort of depends a little bit on the field that you're in. And the decoherence means the lack of this coherence that you have, or this superposition between the two states. That doesn't happen usually the way we think about it. In molecular dynamics, we don't think of it as including that into the Hamiltonian. We couple the system to an environment which is responsible for relaxing the coherence and breaking it up. Okay, but what you see, and this is the key point, is that superposition states are responsible for the time evolution of quantum mechanical properties or observations.